All right, hi everyone. This is Larry Maslino. I'm the course developer for Math325, and I wanted to give you an overview here on Module 1 in the course. So let me come over here to Module 1, and it's on the topic of vectors in space. So let's go over a few items. Let's start off with vectors in the plane, talk about vectors in 3 dimensions, then we'll cover the dot product, cross product, and so on. So to get started here in the course, what we want to look at is creating what are called vectors. And in a simple 2-dimensional way, you could think of a vector as an arrow that has an initial starting point and a terminal point. And we call this a directed line segment because the direction matters for this vector, and that's what's denoted by the arrowhead. And so for a vector, there's 2 important characteristics. There's what's called the magnitude and the direction. And if you've ever taken a physics course, you've worked with vectors probably extensively. Things like forces and velocities and things like that are represented as vectors. Now, with a vector, there is a way to multiply a vector by just a number called a scalar multiplication. So imagine you have a vector v. 2v would be a vector that's twice as long, but pointing in the same direction. 1/2 v would be a vector that's 1/2 as long as the original vector, but again, pointing in the same direction. So multiplying by a constant like this does not change the direction of a vector. It only changes the magnitude. And one thing we're often interested to do is add 2 vectors together. Again, back in physics, you might have wanted to combine 2 forces. And there's a couple of ways you could do it. One way is a graphical way. And the way you could do it is start off with one vector v, take the other vector w and orient it so it's tip to tail. What it means is the starting point of vector w is placed at the arrowhead of vector v. And so the resulting vector is this brown vector here. That's the sum of the 2 vectors. There's another way to do this more algebraically. And one way to do that is to break up a vector into its x and y components. Talk about that in a minute. Well, it's often convenient to orient a vector so the initial point is at the origin. So if you were to take a vector and orient it so it's at the origin, and let's say this arrow ends up being at some xy terminal point here, we use these angle brackets to signify that. So when you see a vector v as angle bracket x comma y, that implies that this vector is situated at the origin and x comma y is the terminal point of the vector. And this x, y components are the kind of the xy coordinates that form this vector. And this makes it easy to add vectors because then you can just add the corresponding x and y components. And so let's look at a quick example. And let me actually go to a 3-dimensional example. So let's go to the next section. And by the way, folks, you'll notice that in each one of these sections, there'll be these different videos to please check out. And when you click this arrowhead here, you can scroll through multiple videos. Okay, so please be sure to check out these videos. All right, let's go to 3-dimensional because that's really, the basis of our course is really going to be a 3-dimensional course. So what we could do here is orient a vector that starts at the origin, but then is projected out into 3-dimensional space. And what we're going to do for this is we're going to set up an X, Y, and a Z coordinate system. So here's the X-axis, the Y-axis, and a Z-axis. And so in this example, we have a vector. Imagine a vector that starts here at the origin, and the terminal point is at this location, 1, -2, 3. The 1 is the X coordinates. So you can see we've gone out 1 here on the X-axis. The -2 is the Y coordinate. So we've gone back. Here's -2 on the Y-axis. And we've gone to a height of 3 on the Z-axis. So that gives us the terminal points. And so again, when we refer to a vector with these angle brackets like this, it indicates that the vector has its starting point at the origin. All right, let me give you a quick example here, because one thing we're interested to do is combine these vectors in a way that might add vectors and also introduce that scalar multiplication. So let me give you a quick example here. Let me write out a vector. Let's call it V. 2, -3, 4. And another vector called W, 1, 0, -5. And the question here is going to be determine the resulting vector from 3V plus 4W. Well, 3V really means take the vector V and multiply it by the scalar. Well, that's going to mean 3 is going to multiply this vector 2, -3, 4. Well, each one of the x, y, z components is going to get multiplied by 3. So this is going to be 6, -9, 12. I'm going to do the same thing for 4w. I'm going to take the vector w and multiply that by 4. So each component gets multiplied by 4. So this is going to be 4, 0, -20. Now I can add these two vectors together. Well, to add the vectors, all I have to do is add the corresponding x and y and z coordinates together. So what I'm going to do here is I'm going to add 6 and 4 as the x coordinates, -9 and 0 for the y coordinates, and 12 and -20 for the z coordinates. So the final answer on this is 10, -9, -8. Okay. All right, another typical calculation that we'd like to complete is something called the distance between 2 points. So imagine you have 2 points out in 3-dimensional space. You'd like to find the distance between these points. This is, of course, very similar to a distance formula that you've seen in 2-dimensional applications. So what it says here is if you have a point, if you have a point x1, y1, z1, another point x2, y2, z2, to find the distance, we'll plug into this formula. So let's do a quick example here. Let's say, let's call it point P is 1, 3, -2. Oh, let me just write these as points. So 1, 3, -2. That's a point in 3-dimensional space. Now let's say point Q is -2, 5, 4. And the question is find the distance between these 2 points. P and Q. All right, well, let's use this distance formula. Let me label these points just to make it a little easier. Let's call this x1, y1, z1, and this is x2, y2, z2. All right, we can plug directly into this formula. First, we need x sub 2 minus x sub 1. Our x sub 2 number is -2 minus the x sub 1 number squared. Now we're going to take y sub 2, subtract y sub 1. That's 5, subtract 3 squared. And last is z sub 2 minus z sub 1, 4, subtract -2, that's squared. All right, now this is just a numerical exercise. That's -3 squared 2 squared. Let's see, this is 4 plus 2, that's 6 squared. So this looks like it's going to be 9 plus 4 plus 36, which works out to be 49, I think, right? 13 plus 36. Yep, that's 49. So square root of 49, which is just 7. So the distance between these 2 points is 7 units. All right, so these are some calculations to help us get started here in Module 1. Let's also go take a look at some other attributes. One thing we want to look at also is something called unit vectors. So let's go look at that. All right, let me scroll down a little bit. And let me come here to different properties of vectors. So scalar multiplication, we did an example of that where we're multiplying a vector by a constant. Vector addition, notice here you just add the x, y, z components together. To find the magnitude of a vector, think of that as like the length of the vector. You just take the square root of each one of its components squared. And here's something called the unit vector. And the unit vector means a vector of magnitude 1 in the same direction as the original vector, say vector v. So for example, if we had a vector here, let's say this magnitude was 5, the unit vector would be a vector in the same direction, but its length would be 1, its magnitude would be 1. So what it says to do is if you want to find the unit vector, take 1 over the magnitude times the vector itself. Let's do a quick example. How about here? So find the unit vector. Let's say for the vector v for -1, 8. All right, well, first thing we're going to need is the magnitude. Let me come up here and let's find the magnitude. That means the length of this vector. So magnitude of v. I'll use this formula right here. So I'm going to take the square root of 4 squared plus -1 squared plus 8 squared. So that's the square root of 16 plus 1 plus 64. And that is what the square root of 81, which is 9. All right, let's find the unit vector then. The unit vector is 1 over that magnitude times the vector itself. But we said the magnitude is 9, so this is going to be 1 over 9 times the vector. So this is a scalar multiplication, so I'll write it as 4 over 9, -1 over 9, and 8 over 9. So this would be a vector in the exact same direction as the starting vector, but it would have magnitude of 1. You can check that, by the way. Take the magnitude of this vector, and you would see that magnitude works out to be 1. All right, let's go to the next section, and let's talk about a topic called the dot product. So the dot product is taking 2 vectors and forming a scalar result. That is a numeric result. And what this tells us is, for example, the dot product of a force vector tells us how much of that force is applied in the direction of the motion of the vector. Another application for the dot product is it helps us measure the angle between 2 vectors. All right, so how do you actually calculate a dot product? And notice the notation here is to just show a dot in between 2 vectors. What it says is you take each component, for example, the x components, multiply them together, the y components, multiply them together, z components, multiply them together, add those results, and that result is the dot product. Let's do a quick example of that. So let's find the dot product for the vectors. Let's say u is 1, 2, negative 3, and v is 4, negative 1, 5. All right, the dot product would be u dot v, and I would take the corresponding components multiplied together. So I'm going to take the x components, which is 1 times 4, multiply those together. Oh, let me get rid of this angle bracket because this is going to be a scalar. This is just a numeric result. So it's going to be 1 times 4. Now I'm going to take the y components multiplying. That's going to be 2 times negative 1. And finally, z components multiplying negative 3 times 5. That's it. I just have to work out these multiplications. That's 4 plus negative 2 plus negative 15. That is 2 plus negative 15. So the answer here is negative 13. This is the result for the dot product. So notice the dot product here is just a numeric result, a numeric answer. All right, let's look at something called the cross product, which is a different calculation. And the cross product is actually going to end up being a vector result. I should also mention finding the angle between two vectors. So if you notice, this formula relates the dot product to the angle of the angle between the two vectors. And sometimes you rewrite this formula to solve for the angle. So we could write it as cosine theta equals u dot v over the magnitude of u times the magnitude of v. Well, this right side is going to be a numeric answer. So we're going to end up with cosine theta is a numeric answer. And then we'll find theta by taking the inverse cosine of that numeric answer. Okay, so that's a way to find the angle between two vectors. All right, let me go to the next section. And of course, there's some worked out examples here in the notes and videos to give you some supplementary examples there. All right, let's go to something called the cross product. And so the cross product is a more complicated calculation compared to the dot product. All right, so let's take a look here. It's a little bit of a messy formula, but imagine you have a vector u and a vector v. If you want to form the cross product, you do these calculations shown in parentheses, and then each one of these calculations in parentheses is going to multiply the I, j, and k unit vectors. So I, j, and k are unit vectors that point along the x-axis, y-axis, and z-axis, respectively. All right, now, when you calculate the cross product, remember your answer is going to be a vector. So you've either got to write it using these I, j, k unit vectors, or you can use the angle bracket notation. Now, there's also something called the right-hand rule to figure out the direction of a cross product. So here is vector u, here's vector v. We'd like to know what is the direction for the cross product. Well, what this right-hand rule says is imagine holding your right hand out. Point the fingers of your right hand along the u vector. So imagine your fingers are pointing along this u vector. Curl your fingers towards the v vector, the direction of the v vector. The thumb of your right hand would be pointing in the direction of the cross product. So imagine you pointed your fingers in the direction of the u vector, curl them, in the direction of the v vector, then your thumb is pointing in the direction of the cross product. All right, let's do a quick example here to work out an example. Let's say we have, let's call it vector A is 3, -1, 2. And vector B, let's say, is 1, 4, -2. So let me label these according to our notation here to make it a little easier. Actually, I guess maybe it's better if I call this U and V to make it a little more consistent with the notation here. Let's call it U and V. All right, well, here is U sub 1, U sub 2, U sub 3. And then here, these components are V sub 1, V sub 2, V sub 3. All right, let's write this formula down here, and we can work out this cross product. So we want U cross V. All right, I'm going to start right here. It says take U sub 2 times V sub 3. Well, U sub 2 is -1 times V sub 3, which is -2. Then we have to subtract. Now I need U sub 3, which is 2, multiplying V sub 2, which is a 4. And this is going to be multiplying the I unit vector. All right, I'll come back and clean that up in a second, but let me keep going. Let's do the J component. Oops, notice this is a subtraction sign here. So subtraction sign. All right, we need U1, V3. U1 is 3. V3 is -2. Okay, now we're going to do a subtraction. Now we need U3, V1. U3 is 2. V1 is a 1. And this is going to multiply the J unit vector. All right, one more to go here. I'm going to come back here. We have U1 times V2. That's going to be 3 times 4 minus U2 times V1. That's going to be -1 times 1, and this is going to multiply the K vector. All right, now we can just clean this up. So U cross V, this is 2 subtract 8. 2 subtract 8 is -6, so it's -6I. All right, down here, 3 times -2, that's -6. And this is a 2, -6 subtract 2, that's a -8J. And keep going. Down here is 12. Subtract a -1. 12 subtract -1 is 13, and so that's going to be 13K. And so that is our final result for this cross product. Okay. Folks, hope this is helpful as you're working in Module 1. If you have any questions, please contact your instructor.